In this video, I'm going to show you how to compute basic indefinite integrals of trigonometric functions. We've got all the derivative rules for the 6 trig functions written down here, and we'll use these rules to come up with integral rules for these trig functions. So starting with the derivative of sine is cosine, if we reverse that, then we know that the integral of cosine is just sine. Likewise, since the derivative of cosine is negative sine, then we know that the integral of sine has to be negative cosine. Going forward, since the derivative of tangent is secant squared, then we know the integral of secant squared just has to be tangent. Likewise, since the derivative of secant is secant tangent, then we know that the integral of secant tangent is just secant. And then since the derivative of cosecant is negative cosecant cotangent, then the integral of cosecant cotangent x is just negative cosecant x, and then since the derivative of cotangent is negative cosecant squared, then the integral of cosecant squared is just negative cotangent. So really, as long as you remember the derivative rules here, then you can just flip them around to get the integral rules. Here's an example. And here we want to go ahead and apply those rules that we've learned previously to compute this larger integral, the integral of sine x plus 2 cos x minus 3 secant squared x. And how we're going to do this is we're going to break it up over each of these terms here and compute separate integrals for each of the terms. So let's start off with integral of sine x, integral of sine x dx. Let's go ahead and write out the rest of the integrals as well. So next up is integral of 2 cos x, so plus integral of 2 cos x dx. And then lastly, we've got our integral of negative 3 secant squared x, so plus integral of negative 3 secant squared x dx. And to clean that up a little bit, let's go ahead and write that again, but let's move all the coefficients in front of the integral, so we just have the trig functions inside of the integrals. So integral of sine x dx, that stays the same, but in this integral of 2 cosine x dx, let's move the coefficient in front. So plus 2 integral of cosine x dx. Same idea with that next integral, so pull out the negative 3 minus 3 integral of secant squared x dx. And now we're ready to solve these integrals. So let's start off with the integral of sine of x dx. Think, what gives you a derivative of sine? Well, that's cosine, but that gives us a derivative of negative sine, so we've got to introduce a negative in front. So integral of sine is negative cosine of x. Okay, let's keep on going to the next integral. So plus 2 times the integral of cosine x. What's the integral of cosine x? Well, what gives us a derivative of cosine x? Well, that would just be sine, so 2 sine of x. And then lastly, minus 3 integral of secant squared x. What gives us a derivative of secant squared x? Well, that's just tangent. So tangent x is our integral, and there we go. Now we're done. Just add our constant of integration at the end, plus c, and here is our indefinite integral. All right, here is another indefinite integral for us to compute. We want to compute integral of 5 secant tangent minus 7 cosecant cotangent. All right, so again, let's just go ahead and split up the integral over these two terms here. We'll have this term first, and to speed things up, let's just go ahead and pull out the coefficient to begin with. So 5 integral of secant x tangent x dx. And then the next term is minus 7 cosecant cotangent. Again, we'll pull out the coefficient in front, so minus 7 times the integral of cosecant x cotangent x dx. So now it just remains to actually compute these integrals. So let's start off with this secant x tangent x. The integral of secant x tangent x, well, what gives you a derivative of secant x tangent x? That's just secant. So the integral of secant x tangent x is just secant x, and keep our coefficient in front, 5 secant x. Same idea with the other one. So minus 7 times the integral of cosecant cotangent. What gives us a derivative of cosecant cotangent? Well, cosecant gives us a derivative of negative cosecant cotangent. So we'll just write down that cosecant, but put a negative on it because we want to cancel out the negative inside of this integral. And then put our plus c at the end. And now let's just go ahead and simplify. So we have 5 secant x, then minus 7 times negative cosecant x. Both these negatives cancel, and we've just got plus 7 cosecant x plus our constant of integration. And there we have it. We're done. All right, here's another example. We want to compute the integral of cosecant squared 2x plus 1 dx. Okay, so this looks like a kind of tricky integral because the input to this cosecant squared function is something other than just x. If this were the integral, say integral cosecant squared x dx, that would be a lot easier to solve. The derivative of cotangent is negative cosecant squared, so the integral of cosecant squared would just be negative cotangent plus our constant. But in this problem here, we've got an input of 2x plus 1 rather than an input of just x. So what do we do? Well, one thing that's tempting to do, but isn't quite correct, is just to say that the integral of cosecant squared 2x plus 1 dx follows exactly the same format as the simpler integral of cosecant squared of x. We just replace x with 2x plus 1. So is that equal to negative cotangent of 2x plus 1 plus a constant? Let's put some question marks here, just so it's very clear that we're not totally sure about this answer. So how can we check this answer? Well, we can just differentiate it. If this is the true antiderivative of cosecant squared of 2x minus 1, when we differentiate this expression, it should give us cosecant squared 2x plus 1. So let's go ahead and try that out. What if we take derivative d over dx of this expression, negative cotangent of 2x plus 1. We'll forget about the constant just because we know that goes to 0 when differentiated. Right, so this derivative is equal to what? Well, let's just go ahead and use the chain rule. The chain rule says that we can forget about the input 2x plus 1 and just differentiate that negative cotangent part. Goes to negative cosecant squared under the derivative, but there's already a negative sign, so the negatives will cancel out, and we'll just have cosecant squared of 2x plus 1. But there's one more thing we have to do. Because we forgot about that 2x plus 1, we have to multiply by the derivative of 2x plus 1 at the end. And the derivative of 2x plus 1 is just 2. So we have cosecant squared of 2x plus 1 times 2. We can just write that as 2 cosecant squared of 2x plus 1. So our answer is very, very close, but not quite there. Is there any way that we can slightly modify it so that it becomes correct? Well, let's think. We want to get rid of this 2 in front of the cosecant squared. So why don't we treat this derivative statement as an equation and just do the same thing to both sides to cancel out the 2. Alright, so let's fill in the left side. And let's just go ahead and multiply both sides of the equation by a half. Now this a half will cancel out this 2 here. And that'll give us just our cosecant squared of 2x plus 1. So that's good. That's what we want the result to be. But now on the left-hand side, we have a half times a derivative. And in order to solve the integral, we need to find a single function that when differentiated gives this result. Right now we have a half times the derivative of some function, but we really want everything to occur inside of the derivative. So can we just move that a half inside of the derivative? Well, yes, that's one of the rules of derivatives. You can factor constants into or out of derivatives. So let's write this. This becomes derivative d over dx of, factoring in that a half into the derivative, negative 1/2 cotangent 2x plus 1, and that's equal to cosecant squared of 2x plus 1. So there we go, that's our antiderivative for cosecant squared 2x plus 1. So the integral of cosecant squared 2x plus 1 dx is equal to just negative 1/2 cotangent 2x plus 1 plus our arbitrary constant of integration. There we go. Now, a few things to mention before we end. First of all, this method will work on any basic trig integral which has a linear argument, because applying the chain rule to that linear argument will just result in multiplying by a constant at the end. So you can just multiply by the reciprocal of that constant on both sides to cancel it out. Now, the really important thing, though, is that this only works for linear arguments, because the derivative of the linear argument is constant, meaning that we can factor into the derivative on the left-hand side here. If you tried to apply this method for, say, a quadratic argument, you'd end up with an x term in your derivative. And sure, you could multiply by the reciprocal of that still to cancel it out on the right-hand side, but on the left-hand side, you'd have an x term instead of just a constant. And it's only constants that you can factor into the derivative. If there were an x in this expression 1/2, then we couldn't factor it into the derivative. So just remember that this method works for linear arguments, but linear arguments only. Alright, so now we know how to integrate trigonometric functions. And in the future, we'll learn more methods of integration that will allow us to integrate even more complicated functions.